Chapter 8 is all about gases. There are a variety of properties of gases that we're going to be talking about, one of which is pressure. Pressure is defined as force per unit area. We could write the definition as an equation. Pressure P equals force F divided by area A. Something to keep in mind as we talk about pressure is that the atmosphere is always pushing down on us and our reactions. The atmosphere exerts pressure, and it's actually not insignificant. In fact, it is the same amount of pressure as a bowling ball pressing on the area the size of your thumbnail. It doesn't feel like we're being crushed by a bowling ball all the time because we're used to it, and our bodies work well under this amount of pressure. If we were to have a bowling ball on our thumbnail, that would actually be doubling the amount of pressure that our thumbnail would be feeling. There are a lot of different units for pressure. The Pascal is the official IUPAC unit, and it's equal to 1 Newton per meter squared. Newton is a unit of force, meters squared is a unit of area. So Newton per meter squared is force per area, which you'll recall is the definition of pressure. The kilopascal, which is 1,000 pascals, can be a more appropriate size for some applications, so you may see pressure in kilopascals sometimes. Pounds per square inch is abbreviated PSI, and you'll hear that unit in popular culture. Just for reference, the air pressure at sea level is 14.7 psi. Another unit of pressure is an atmosphere. 1 atmosphere as a unit of pressure is equal to 101,325 pascals. Try not to confuse atmospheres, which is a unit of pressure, with atmospheric pressure, which is the amount of pressure pushing down on something by the atmosphere. At sea level, atmospheric pressure is approximately 1 atmosphere. On a mountain, atmospheric pressure is less than 1 atmosphere. In other words, less than 101,325 pascals. Under the ocean, the pressure could be greater than 1 atmosphere. In other words, greater than 101,325 pascals. Most of our experiments are going to be assumed to be done at 1 atmosphere of pressure. 1 bar is equal to exactly 100,000 pascals. The bar and the atmosphere are very similar sizes, but the bar is linked up with the pascal to be an even multiple of 10. It's exactly 100,000 pascals instead of 101,325. Bar is a common unit used in meteorology. Millibar is another version we could use. 1,000 millibars is equal to 1 bar. Another common unit that you'll hear referred to is inches of mercury. An inch of mercury is equal to 3,386 pascals. The inches of mercury unit is used on weather.com, for example. Torr is equal to 1/760th of an atmosphere. In other words, 1 atmosphere is equal to 760 torr. This is going to be a very important and common conversion that we're going to use in this chapter. The torr is named after Torricelli, the inventor of the barometer. Our last unit of pressure is millimeters of mercury. 1 millimeter of mercury is approximately the same thing as 1 torr, so I'll be using them interchangeably. The way we measure atmospheric pressure is with a barometer. A barometer has a tube, usually made of glass, inserted into a pool of liquid. The atmospheric pressure pushes on the pool of liquid and causes some of the liquid to rise into the glass column. The height of the liquid in the column corresponds to a particular pressure. We can calculate the amount of pressure using the equation P equals HdG, where P is the pressure in pascals. Remember, a pascal is equal to 1 Newton per meter squared. Another conversion that we can use for pascals is kilogram per meter times second squared. As you check the units in your calculations, make sure you end up with units of kilograms per meter times second squared to get your answer in pascals. You may or may not need to also convert to kilopascals. In order to get units of pascal for pressure, the height, h, must be in meters. D is the density of the liquid and must be expressed in kilograms per cubic meter. Most columns use mercury as the liquid, but it could be a different liquid such as water. The reason why mercury is the most common fluid used in a barometer is that it's very dense. Since the density is high, then the height of the column can be lower to measure the same amount of pressure. We can have smaller barometers made of mercury compared to water, which would need a much larger barometer. The last part of the equation is G, the gravitational constant, which is 9.8 meters per second squared. Just like with all the other equations we use, it's going to be really important for the units to cancel out properly. So we need to get all the variables into correct units before we plug them into the equation. Here's an example of calculating pressure with a barometer. We're trying to show that atmospheric pressure is equal to 760 millimeters of mercury, and the density of mercury is given as 13.6 grams per cubic centimeter. The first variable, H, is height of mercury in the column. The height of the mercury is given in millimeters, but we need to get it into meters before we plug it into our equation. We set it up so that millimeters cancel out. We multiply 760 by 10 to the minus 3 and come out with 0.760 meters. D, the density, is given to us in units of grams per cubic centimeter. We need it in kilograms per cubic meter. This conversion is going to be tricky. First, we need to get grams into kilograms. So grams will go on the bottom to cancel out, and kilograms will go on the top. 10 to the third is the same thing as kilo, so 10 to the third goes next to our base unit of grams on the bottom. Then we need to get cubic centimeters into cubic meters, and this is the really tricky part. Since we have cubic centimeters in the denominator of our original unit, we're going to need to have cubic centimeters in the numerator of the conversion factor in order to cancel out. We write our usual conversion factor going from centimeters to meters. 1 centimeter is equal to 10 to the minus 2 meters. Then, to get it to be cubic, we're going to cube the whole conversion factor. When we cube the whole conversion factor, that not only cubes the units so that we get cubic centimeters and cubic meters, it's also going to cube any numbers that are inside the conversion factor. So that 10 to the minus 2 gets cubed. And so we end up with 10 to the minus 6 in the denominator of that conversion factor. 13.6 divided by 10 to the third, I hit enter just to be safe, then divided again by 10 to the minus 6, is 13,600 kilograms per cubic meter. Now we have everything in the correct units to plug into our P equals to HDG equation. We plug in our height in meters, we plug in our density in kilograms per cubic meter, and we plug in the gravitational constant, which is in meters per second squared. We come out with 101,292.8. Meters in the height and gravitational constant cancel out with 2 of the 3 meter units in the density, leaving us with units of kilogram per meter times seconds squared. This is the same thing as the Pascal, so our final answer is 101,292.8 Pascal. Recall from our slide on units of pressure that 1 atmosphere is equal to 101,325 pascals. Within error, this means that the pressure is 1 atmosphere, which is what we would expect at sea level. What pressure is exerted by a 75-meter high column of water, which has a density of 1.00 grams per cubic centimeter? The gravitational constant is 9.80665 meters per second squared, and 1 atmosphere is equal to 101,325 Pascal. Is it A, 687 atmospheres, B, 7.26 atmospheres, C, 7.4 times 10 to the 7 pascals, or D, 7.0 times 10 to the minus 5 atmospheres? The correct answer is B, 7.26 atmospheres. This problem is done basically the same way as the previous, but with a few differences. One is that we don't have to change the height to meters, because it's already given to us in meters. The other is that our column is filled with water instead of mercury, so the density is different. You're still going to have to cube the whole conversion factor so you can go from cubic centimeters to cubic meters. Again, the 10 to the minus 2 gets cubed. If we want to measure the pressure of gas trapped in a container, we would use a manometer. There are a few different types of manometers. They could have a closed end or an open end. The equations for measuring the pressure are pretty similar to the one for a barometer, but there are some modifications. If there's a closed end and a vacuum, the equation is the exact same. Pressure equals H times density times the gravitational constant. In this figure, density is represented with the Greek letter rho. If there's an open end, start with the atmospheric pressure and either subtract HdG or add HdG, depending on whether the liquid in the column level is lower on the side that's open to the atmosphere or higher on the side open to the atmosphere. If it's lower on the side open to the atmosphere, subtract HdG, and if it's higher on the side open to the atmosphere, add HdG.